So I'll start from summary. So yeah, I'm going to start with an overview of distributed database feature and an overview of Aerospike. And then going from there, I will give an example of how we test our product in Aerospike with the demo. With this presentation, I hope to show an approach to capture characteristics of a distributed database, and from that, give an idea on how to test distributed systems in general. So a distributed database is a database in which data is stored on multiple computers across different geolocations. In a distributed database, nodes communicate and coordinate with each other by passing messages to one another. So they're aware of each other's state. It's designed so that to an end user, it'll appear as a single coherent system. These are some of the benefits of a distributed database. Scalability is one of them, since nodes are relatively behaving independently. It's easy and inexpensive to add node when there's a need. A distributed database also possesses reliability because a cluster of a database is made of many components so that work together. So it means generally more fault tolerance. As opposed to in a centralized database, a small failure on the system, on the machine, can mean a significant disruption. High performance is another benefit of distributed database. On one hand, workloads can be processed concurrently on different nodes altogether, so it means more efficiency. On the other hand, servers can be distributed to the locations that are closer to end users, so this reduces network latency. So to think about how to test a distributed database, this is a summary of some of the difference between a distributed database and a single computer database. In a distributed database, nodes are loosely independent. With that being said, there's still communication among nodes in the same system. This is mainly to get to be aware of each other's state. And shared nothing architecture, which Aerospike has this architecture. It means nodes have their own memory and storage. Updates can be handled by one node independently. There are some specific challenges for distributed database. So this is some of the ways how things can go wrong. For example, one or more nodes in the system can go down, can fail, and on the network issue is another significant challenge because of the fact that nodes rely on network to communicate with each other in a cluster. So any network disruption means a disruption to the system. This can include connection failure and slow network, which will introduce latency. So when testing an application that runs against a distributed database, we want capability to control the whole cluster as a whole, as well as controlling each node individually. And we want to run the client or application or any other tools separately from the server environment. We also want the capability to trigger or simulate various cluster fault situations on the server side to see how the system behaves. Okay, now let's talk about my day-to-day job. This is a brief introduction of Aerospike. I work at Aerospike. It's actually not a rocket ship company, but a database company. There is an interesting story behind the company name, and briefly, the word Aerospike refers to two of the rocket engine components, both of which has rich meaning to the database. Those components in rocket help the rocket reach speed and reliability at lightweight and low cost. So this is what the database is named after. Aerospike database combines scalability with strong consistency. As for data model, it supports key value store as well as document-oriented data models. So Aerospike has a characteristics of general distributed database I just gave an overview with. The architecture involves client layer where APIs are implemented, and clients are generally cluster aware, meaning they know where data should reside in which node of the cluster. And clustering layer, this is where clustering communications are managed. Things like data migration, failovers are handled, and also cross data center replication is handled, where where data can be shipped from one cluster to the other. Then comes data storage layer. This is where hardware is involved. So data can be stored in, for example, DRAM, flash, PMAN, SSDs. These two links are some of the main pointers to find out more about us. Okay. So now let's talk about testing our product, testing this database. So our coverage of testing include server-side testing. This includes all the features and server functionality testing. A significant part of this server-side testing is simulating various situations of cluster fault. And I want to mention performance testing is also a big part on server-side testing. And then client testing, we run clients on different Linux distributions and mainly run functionalities of the clients against the server, and also tools testing. So all of these different categories of testings are actually based on similar infrastructure. The components should involve a server cluster to be running, and the client and tools or other applications to be running separately. We use containers for this kind of testing. Specifically, we use Docker. So Docker is a platform that uses OS level virtualization to package software into containers. Each containers are separated from one another, and they also allow sharing file systems. So in our testing, this can come convenient when it's okay to share some of the files, like server configuration. We run clean instances of Aerospike server on Docker containers. The instances are basically reproducible conditions and environments to start the server. The parameters of these reproducible conditions include server builds, server edition, server configuration, and initial cluster size. So all these combinations make up for a very complex matrices of tests that are run day to day. And we use other containers, which are called test containers, that are separate from server containers. Clients and tools are running on these containers to interact with the server, and some other programs are made to control Aerospike server. They can control the whole cluster or individual nodes by stopping or starting server nodes to simulate a node outage or new nodes joining. They can also be used to control network communication among nodes. For simulating this network fault part, tools like traffic control and IP tables are used. IP tables is a tool that lets user to configure IP packet filter rules on Linux. Okay, so before I go into the demo, I'm going to go over data distribution and replication in distributed database. Let's look at this simple example. Suppose we have 3 instances of Aerospike server running. Namely, it's a 3-node cluster. So we have node 1, 2, 3. And across the whole cluster, we configure the replication factor to be 2. So that means for any record we want to load into the cluster, there will be 2 copies of them, including the record itself. Suppose we have these records that we want to load right into the server cluster. First of all, the partition algorithm from the server side will decide which record goes to which node. And because we have replication factor as 2, each record will have a replication. Replications for a record will always be on a different node from this record. Or I should say all replications of the record will be on different nodes. So for those 3 records we want to load into the system, we end up having the distribution of them across the cluster like this. So hopefully this gives a basic idea of data distribution and replication. Now it's demo time. So in this demo, I'm going to show in a raw environment how we test this particular database and give a sneak peek of what I do in the general testing based on doing stuff automatically on Docker containers. I'm going to bring up a 3-node cluster with the client running on test containers, loading some data to the server. And then I'm going to manually disrupt the server cluster by stopping and starting some nodes. And then I'll let you observe some cluster migrations and cluster size change, and also data redistribution happening. So next, I'm going to start containers. I'm going to show you a screenshot of a terminal window. Our test system is set up that a command will automatically fire up relevant Docker containers. So by running this command test runner, containers should be up now. Now let's see what containers are running by using Docker PS. We can see there are 4 containers running, out of which 3 are Aerospike containers, 1 Aerospike node running on 1 container. And there's also a test container. So let's see what's happening on the test container. There's a script right now running on test container. On the screen, what you can see is part of the script where a Python client is loading some records to server. So for demonstration purpose, I'm making the data loading very slow, 1 record per second. In our actual testing, the data loading involved is much bigger. Sometimes tens of millions of records will be loaded within a short amount of time. Okay, so this is printouts from the test container from that script. So we'll see that records are being written. Let's fast forward. Oh, oops. So meanwhile, let's see what's going on from the server side. I'm going to show you the view from one of the 3 nodes on the server side. So on server node 0, this is a log from that node. There's a lot of information in this log, but let's only focus on object counts here. We'll see that object counts are slowly increasing. Let's fast forward. So the script will stop when 100 records are loaded into the server. And we'll let the server containers keep running. So again, on the same node, node 0, we can see that the object count here is 69. And cluster size is 3. It should be, yeah, here. So cluster size is 3, it says. So I'm going to explain a little bit about object count here, remembering the data distribution and replication. We load 100 records into the server, to the whole cluster, and each has another replication. So that means 200 records distributed across 3 nodes. They're always approximately evenly distributed. So that means each node has 1/3 of 200 records. So 69 is about that number. So next, let's try some cluster disruption. I'm going to bring down a node from the cluster. We'll send some command to one of the server containers to stop Aerospike daemon on that container. So in our testing, those commands are put into scripts for automation. Okay, now so node 0 is stopped. So this is the view from another node which is still running, node 1. Now that we have stopped node 0, this is what I'm going to start is immediately what's happening after node 0 is killed. So a lot of things are going on. There are many about reclustering and migration, which are triggered by one node leaving the cluster. Like we'll see migrations. And if I go back there, we'll briefly see that applied cluster size 2. So cluster size changed from 3 to 2. Okay, migrations complete. And when we look at object count, it goes to 100. So thinking about data distribution again, because now those 200 records are distributed across 2 nodes instead of 3. That's why the counts are going from 69 to 100. Now, after that, I can bring up the node back up. For the same node, Aerospike A0, node 0, again through the command send to the Docker container, we start this node. Okay, let's look at the view from node 1 again. It's similar to the previous view. Immediately, a lot of printouts, a lot of things going on after a node joins, and it says applied cluster size 3. And when we look at object counts, it's back to 69 again. And now migrations are complete. So all these things happening, are they expected or not? In this situation, everything's behaving as expected. Cluster size change, it means when a node is down, the cluster can detect it. And when a node joins, the cluster is also aware of it. So the cluster size are always changing to the right number. And also the data distribution is behaving correctly. So in this demo, things are, the cluster is doing the right thing. Basically in this demo, this is, again, this is what I showed you. A cluster is brought up, and I showed you containers, including server containers and test containers, loaded some records, and introduced the disruption to cluster, and pointed out triggered migrations from the server log, and cluster size change and object count change. Okay, so that's the end of the demo. So in this presentation, I talked about distributed database and how it's different from single machine database. We use containers to simulate those distributed environment. And I also talked about this data distribution and cluster disruption. I used a demo to explain these two things, data distribution, and showed what happened with cluster disruption. Hopefully from the example here, more ideas about testing distributed database can be started from here. That's the end of my presentation. Questions?
Thank you, Minting. I think that was so spectacular to watch, especially the demo part.
Thanks.
So there are not yet any questions. I think I can just ask my own curiosity. When a node goes down, where does the data being rewritten in the other nodes come from? Since the node has already gone down, right?
Yeah, I mean, where does the data migrate from?
Yes, so the node has gone down. So the node has record C and D. So where will record C and D come from for them to be rewritten in the other nodes that are still up?
To my understanding, there's an algorithm to decide how records are distributed. I think it's based on some hashing. So this is deterministic. So the records are mapped into different nodes. When cluster changes, when the node is reduced or added, that the data will be remapped. So that's the starting of the migration. Yes, so that's my understanding, and I'm sure there's a more detailed explanation of data migration and distribution from the website, and also on the URL I linked under my email.
All right, thank you. Because my own understanding was that if a node goes down, that means the records in the node have also disappeared. So I was just wondering how the records will be gotten to be rewritten in the other nodes, because the records have also disappeared with the node.
Oh, I see what you mean. Okay, yeah. So this is actually a slightly different question. So because in most of the times, if the replication factor is not 1, if it's 2, then that means if one node goes down, then still another copy of the record is somewhere else in the cluster on some other nodes. So actually, it means the cluster still has that data, and it can redistribute it, do some redistribution to decide where the records should reside after this disruption. Did this answer your question? So if to my understanding, if there's only one copy of the record and you turn a node is down, then there will be some data loss. But if there are 2 copies or more, then that means more copies are on other nodes. So the data is not lost, and they start to migrate across the cluster. Yeah, I hope that explains some of this.
I guess we can take down your contacts and maybe tweet you or email you in case we have questions arising beyond here. Otherwise, we will be having another 10 minutes break before our next talk. Thank you, Minting. Thank you, everyone.
Thank you.
Yeah.